we were discussing different applications of robotics, different types of robots. So we are continuing from where we stopped last time. Um, One of the last things we discussed was about planetary exploration robots. These are actually geologists, robot geologist. That is the most accurate uh, description of these robots. They are doing some sort of geological experiments, tests on different planets like Moon, Mars, etc. And they drill the soil, drill the rocks, they collect air samples and do chemical analysis, what sort of chemicals are there and their relative abundance. And if it comes to rocks, they drill and get the samples from the top surface of the rocks and 1 centimeter below the top surface, 2, 3, 4, 5 centimeters below the surface. Then what they're doing is if you get the samples from the rocks, say 1 centimeter at a time and going deep down from the surface, actually you are testing the atmospheric conditions millions and millions of years ago. So this way you can actually write down the story of that planet across millions of years, what was there millions of years ago, right? Uh, so it's extremely important. So that is the separate story. But when it comes to robotics, you need to figure out how you can design and build a robot like that, okay, to do that kind of tests. In addition to that, these robots need to get very clear photos of the planet to figure out the color, the nature, the surface structure, everything very, very closely, like you actually went there, right? So if you look at some of these images sent by this Curiosity rover and the rovers even before that from Mars, you actually feel like you are there. When you see just the photos, when you combine these photos, you can actually generate what is called the panoramic mosaic of the planet. Then if you just see that without anything here on Earth, you actually tend to feel that you are there. So that is the kind of high definition, very, very clear images. First time we were able to see those images. In addition to that, the robot needs to be very stable. So therefore, you need to have very stable platform. And the wheeled mechanism, 6 wheels, and their rocker bogie platform. You can study a bit more about this mechanism. This particular mechanism can go over big obstacles, more than twice the size of, probably about twice the size of the wheel. Okay, so imagine a vehicle which can go over an obstacle twice the size of the wheel itself, right? Uh, then it has to be fully autonomous, right? Because you have no way to look at what's in front of the robot and then drive and steer the robot from here, from the earth. Not possible. So it has to be fully autonomous. Okay. So, and you have never been there before, right? First time you are there. So how you can build an driving and steering or particular navigation algorithm for such a robot, right? These are all complicated problems in robotics. Okay. Right. Think about it, because I'm not just telling you this as just as a story, but in a way it's a story because, as I always say, whenever you learn a subject, you need to learn the stories. Okay. A lot of people don't understand that. They jump on the theories, the mathematics, the physics, etc. That's very important. I'm not discounting that. But you will be missing a lot of very important part if you do not know the story. Okay. The story makes you build interest of the subject. Every time you read about, let's say, the pioneers of different areas like Albert Einstein, Richard Kalman, Bellman, etc. Right? You actually tend to fill the gaps in your memory, right? About that subject. So therefore, it's very important to know about the stories. Then you can actually connect your theories to the real world. Okay. And also, I will be testing your memory, your awareness about these robots. I'm not just asking you to solve mathematics, right, in the paper. Uh, very closely related to the planetary rovers is what is called the all-terrain mobile platforms. All-terrain, which means can you design and build a robot which can handle any terrain, right? Like flat lawn or grass, unstructured, very rugged terrains, like what you see on the right-hand side. Uh, so how you can design and build a robot? It's all depends on the mechanical design of the platform and also the control uh, system that you bring in, right? Last week, we look at some of these platforms. On the left is our design, what we have built many, many years ago at electronics department. Is a holonomic mobile platform which can actually move anywhere, any direction without changing the heading, right? Say, look at your vehicle, the cars, right? When you want to park the vehicle in a tight space, you have to drive it back and forth, back and forth, back and forth many times, right? But what if you can drive the vehicle parallel to uh, uh, the parking lane, just like when you're driving, and then stop right next to the parking lot, and then you turn the wheels 90 degrees to your left or to your right, and then car moves 90 degrees lateral, right, to the direction. So you park there, and when you get your car out of the lot, also you drive 90 degrees, you turn the wheels by 90 degrees, right, and then drive, get out of the parking lot, you can drive. So the problem is the modern cars, they cannot uh, turn the wheels 90 degrees. Okay, that's the problem. The moment you have this mechanism, you don't have parking problems anymore. Then on the right hand side, I think we saw this last time. Um, the wheels and legs combination. Everybody knows about legs, right? Uh, two leg, four leg, six leg, like that. And everybody knows about wheels also, right? Two wheels, three wheels, four wheels, five wheels, whatever number of wheels. If you look at these two platforms, legs and wheels, if you look at just legs, for example, the legged locomotion is good for unstructured environments, unstructured, okay, unstructured. So wheels cannot actually handle unstructured environments because wheels can get into a ditch and then stuck there, and there's no way to get out of that. You have seen many vehicles in mud and ditches and pits and all. It's difficult to get out of that. Okay, whereas legs you can take very easily out of these situations because it's not a rotating thing, right? You can lift the leg and step by step you can move forward. However, the problem with the legs is that if you look at very flat environments, kind of structured environments, wheels is the best because wheels can have very high speeds on structured environments, right? Where legged mechanism is not very efficient in those areas. And also controlling the stability of legged platforms is a bit difficult than wheel platforms. So the two different platforms, they have their pluses and minuses. Okay. What if you combine these two together? Then we call it wheels and legs, or wheel leg design. Here you can see the legs, but they are rotating legs. So you have the rotary mechanism as well as the legged locomotion. The traction of legs is there. So I think we saw this last time. The platform is fantastic, and it can handle different types of terrains very easily. Now today, I'm going to show you another area in robotics, that is obstacle avoidance. This has been a very interesting area uh, about 2-3 decades ago, right? Obstacle avoidance is a buzzword in robotics, right? Uh, Now it's not so, but still it's a very fantastic area for robotics research. When it comes to obstacle avoidance, people started developing algorithms to avoid static obstacles. What do you mean by static obstacles? It's like if you look at a classroom, the tables and chairs are not moving, static, and the robot or the students walk, avoiding any collision with those obstacles, right? Chairs, desk, etc. So that is static environment, and the robot has to avoid collision with the obstacles. So static obstacle avoidance, relatively easy. But if you look at the real world, it's not always static, and often it's dynamic, which means there are moving obstacles. If you look at a hospital, right, except for the beds, etc., there are people who are walking, right, here and there. So if you design a robot to move, right, in a hospital, it needs to have the ability to avoid collision with dynamic obstacles, right? They are the people also are considered dynamic obstacles. Okay, so that problem is a bit difficult because you need to constantly look at the obstacles around you and particularly figure out anything that comes closer in a collision path. Okay, you have to figure that out and avoid it. So I'm going to show you something we did again not very recently, sometime back with Stanford University Robotics Institute, Professor Khatib. There, uh, um, there was a very famous obstacle avoidance algorithm developed by Professor Khatib at Stanford. It is basically creating an artificial potential field around the obstacle. Now, if you look at this one, this is an obstacle. This is the robot, right? And this obstacle, around this obstacle, we create a potential field. It's like a electrostatic field, like a charge particle. Okay. So robot is also, let's say, assume for a moment robot is an electron. Obstacle is also an electron. So electron, they repel each other. You know that, right? They do not attract each other. So this repulsion force can be used for collision avoidance. So what Professor Khatib has proposed is that, okay, we will look at the location of the obstacle, and we know the location of the robot in, let's say, XY coordinate frame, and we can figure out the distance and the direction, okay, and you generate a force vector away from the obstacle, right? So this is an artificial thing. There's no physical potential field, okay? These are all artificial. Everything is happening inside a computer. And in the same coordinate frame, you generate this uh, repulsive force, UP, okay? and this is the force, artificial force on the robot. So if you are the driver, now you have to drive the robot and steer the robot towards UP. Okay. So when you do that, you make sure you are not going to collide with the obstacle. So that is the whole purpose. Now, the robot has other objects, right? Objectives rather, in addition to avoid collision. So avoid collision is for only for the safety uh, assurance, but the robot is there for something else, to perform a useful task, right? Not to keep avoiding obstacles all the time. There is a target, there is a goal that it has to go. Like for example, here you can see the goal here. Robot has to go to the goal, right? So you also have goals in your life, right? You want to achieve certain goals. Now, while you are trying to achieve the goals, you have to sustain, you have to survive uh, imminent collisions, imminent problems, right? So you have to survive the day in order to achieve your goal tomorrow. So this is the concept in mobile robotics. Avoiding avoiding collision is extremely important in the short run, but it's also important to achieve the goal in the long run. So this is a long run objective. This is the short term uh, defensive or aversion, right, of the collision. So when you combine these two together, you can generate obstacle avoidance algorithm, right? And it works. So when there's an obstacle, you move out of the away from the obstacle, and when there's no obstacle, it tries to reach the goal, and these two works together at all times. So we studied that problem and then figure out, okay, this is working, but it's very inefficient. It's very inefficient, right? Uh, Therefore, what we did was we developed what is called a dynamic velocity dipole field method. So there we introduced not a static field, but a static electrostatic field. This is like magnetic field. The two field structures are different. The dipole field has a direction. So if you know the direction of the robot, you can generate these field lines, and you can mathematically uh, define them as ellipses, right? Because everything has to be analytical. So the field line should be mathematically defined. So we use ellipses because there's no need to use exact magnetic field lines, right? Because this is not a magnetic field problem. This is obstacle avoidance. So you could have taken anything that is reasonably good. So we use ellipses, right? Like that. So the elliptical field lines are like that. So therefore, the repulsive force, right? In this case, there's a repulsive force. In this case, there's a driving force, not radially outward, but along the direction of the magnetic field line. You can see the difference here and here. This is the force from the static potential field. This is the force from the dynamic dipole field. Okay. So when you combine this behavior also, the performance of the obstacle avoidance uh, improved quite a lot. Improved quite a lot. So um, the new algorithm where you use the classical potential field and also velocity dipole field together with the goal seeking force, when you combine these three forces together, you get the resultant force, and your driving mechanism, steering mechanism try to align the robot and drive it uh, along the direction of the resultant force, that is combined force of these three vectors. Okay, so that's how it works. I'm not sure whether this uh, let me check whether I have some videos to show you. Yes, just look at this video. This is um, velocity dipole field. Right, you can see over here. Actually, we experimented this using robot soccer test bed. You can see the soccer field. This is designed for robot soccer. So I use the same platform to test this algorithm. So this is the obstacle which is traveling from here. This is the robot which is trying to achieve the goal. Goal is over here. So when there is no obstacle, the robot goes straight to the goal. But now there is an obstacle which is placed over here, and it is actually driving with the same speed as of this robot. Okay, so if you just drive this robot towards the goal blindly, there's a sure collision right here. Right, there's a sure collision over here. So the robot has to avoid collision with the obstacle which would happen right over here, unless the robot uh, consciously avoids it, right? And the obstacle doesn't care about that. It drives straight. So let's see what happens. So you can see it's almost there to be collided. Okay, see, it goes very close but turns and go around it. So that type of collision avoidance was uh, um, almost perfect at that time, many years ago. So this is when the robot, the obstacle uh, travels with similar speed uh, to the speed of robot, right? Uh, Going behind. So robot does not try to um, avoid the collision by going in front of the obstacle. It goes behind it, right? This going around the obstacle is actually coming from uh, this behavior. Look at the field lines here. Look at this field line here. So when the robot goes very close, it follows the field line. So it goes around uh, the obstacle. You saw it in the experiment, right? So let me show another video where we had uh, fast obstacles. So this time the obstacle is twice as fast as the robot, twice as fast as the robot. So you can see uh, if the robot does not avoid the collision consciously, there's a sure collision somewhere over here, right? And that point, uh, the distance to this point from the robot's position, let's say it's x, and this distance is 2x. So in the same time, the obstacle travels 2 times the distance that of the robot. So they are uh, meant to be collided somewhere over here. So let's see what happens. Now this time you can see the robot, right, takes a turn, right, when the obstacle is actually a little far away, right, not like the earlier case. Earlier case, the obstacle is not that fast, but now it's very fast. So robot cannot take any chance. So it tries to take this aversion behavior, right, well in advance, like that. Then it avoids, right? So we tested this for various velocities, various positions, and every time it avoided the collision perfectly. So that's about it. Okay, so collision avoidance, dynamic obstacles is another very significant area. Then the next topic is robot vehicles, autonomous vehicles, right? Uh, you have seen autonomous drone, like for example, drones are fully autonomous, right? So they are flying robots and there are underwater robots, right? Somewhat or fully autonomous in certain cases. But it's very complicated to put a autonomous car on the road because there are people there. Okay, there are people there, so you have to be extremely careful when you have an autonomous vehicle on the road. You remember a couple of years ago there was an accident, right? An autonomous vehicle ran over somebody, and I think the person was killed in that accident. And you can see there are a lot of accidents on the road, right? People get killed every hour, every day, but nobody is saying that, okay, no more vehicles on the road, right? Nobody's saying that. But if you have a autonomous vehicle and if it hits somebody, then the government say no more, right? Enough is enough. So this is not correct. This is not correct. But there's a point when there's a person, right? When there's a person, it can be mistakes, it can be various things. Then there are court cases and it goes like that. So when it is an autonomous vehicle, right, uh, the law does not accept the technology. That's the point. So if it is done by a human, then you take the actions and proceedings, but you're not, nobody is telling, okay, to stop that service or whatever. When it comes to entirely technology thing, is completely opposite. There's a zero tolerance, nearly zero tolerance from the authorities about autonomous things uh, uh, affecting people. So the robot vehicles, right, will be there on the roads, but not as fast as you would think. So let me show you a little video on that. I'm not sure whether this is linked properly. Uh, oh yeah, it is. The car is driving autonomously. You can see the line. I think the car is following the line. You know that center line? And this is obstacle detection and avoidance. You can also see some of the sensors attached to the car. There are laser range sensors, there are lidars, there are sonars, there are radars, there are cameras. Yeah, you can see some sensors looking on the road, right? So I think this technology has made a serious development in the recent times, and it will only be improved. And at some point in time, they will really be very trustworthy technology on the road. Just a matter of time. And also, I have heard that this has some benefits that usually we do not understand in the first sight. For example, look at blind people, right? Look at blind people. They can't drive their vehicles, right? Um, but if they have this kind of vehicle at home, they just want to get in the car and ask the car to drive them to a certain location. Understand? So uh, that that will change the life of blind people forever. So they don't depend on anybody anymore, right? They can go anywhere and they can go to the shopping mall, they can go to restaurants, and at that point, how to get into the restaurant and get the food, order the food, that's a separate problem. That's not a big problem. Getting from point A to point B is a very difficult problem for blind people and also for disabled people, right? Blind and disabled. So therefore, this is a significant development if you look at the welfare robotics part. So therefore, I consider this more as a welfare robotics technology development rather than just autonomous vehicles. Then together with that, the robot vehicles, there is another area that is telepresence robot. Telepresence robot. So what are they? What are they? So again, as I mentioned earlier, the stories matter a lot. Stories. So let me tell you a little story. Many years ago, more than a decade ago, I think, there was an incident in UK, I guess, and there was a little boy in a family of three kids. Okay, parents and three boys, I think. One of them, maybe the youngest, uh, uh, got um, like he was diagnosed with some cancer or something, right? And he underwent a surgery, very critical one. And after the surgery, he had to be in perfect isolation. Nobody could see him and bring any of the germs to him, right? Because it could have been very dangerous for him. So he was in total isolation for about maybe a few months, 3 months or so, and nobody could see him. So at that time, what was there was this robot. You can see here this robot. Uh, this robot was with the kid in that room, and this robot is a telepresence robot. So anybody can log into this robot, right, over the internet. Maybe his brothers, parents, right, and this robot, you can drive this remotely, and this robot moves around, and this kid in the isolation felt like there was somebody next to him in the room. There was somebody like a pet. Okay. Otherwise, it could have been total isolation. Because of the robot, he didn't actually feel in isolation. He has spoken out after coming out of the isolation, how it was like in the isolation, and he said praise about this robot. He actually felt his brothers and parents were there with him, right? Uh, and also, there are some very busy parents, not in Sri Lanka, maybe in other parts of the world. They are not there with the families. They are not there with the kids because they have to travel quite a lot, right? And giving a telephone call is very fundamental, very basic, and is not going to replace the presence of a family member, right? Now you can have video calls, and video calls also is on a screen, and you have to go there, and then you can see your friends, family members, father, mother, etc. But what if you have a robot in your house which has two wheels and which stand like a physical thing and it moves around? And when you are in your room studying, the robot comes to you. A robot is actually your mother, your father, your friend, or somebody, and he speaks to you. This is better than just a video call. Understand? So you feel better. It's not a replacement for the physical presence of the person, but this is better than just a video call. Okay. So the tele robots, there's a market also for tele robots, the telepresence robots. The word tells you make your presence remotely. Okay. So let's see this video on one of these commercially available telepresence robots. That is double. So there you can you saw that the person from home is connecting right, connecting to multiple places at the same time. He goes to the class, to the lecture. Can go to his workplace and talk to a technician. And also he can go to a art exhibition or something with his wife entirely remotely. So the future, the world will be full of these stuff, robot vehicles, telepresence robot, and surgery, telesurgery systems, right? Is all about technology, safe, efficient technologies, right? So that's why this uh, is a very important subject for everybody to know about, right? Okay. So that's all for the first lecture, which is entirely on different areas in robotics. Now, out of these areas, let me pedal back, right, to show you the list again, right? I explained you almost everything in robotics, right? I now want to show you this one, the areas, different areas in robotics. But for the most part of this module, we are going to look at this one, industrial robots, because this is the core of robotics. This is the first area in robotics and also the most commercially exploited area in robotics. Most of the mathematics, most of the software, they were built around this area of robotics. So other areas are basically research areas, right? Even though the title says research areas, this one is much more commercially exploited area, industrial robots, right? Or robot manipulators. Other areas are bit too complicated to say that it needs a lot of algorithms, a lot of sensor fusion, and a lot of research. So it takes a little while for those areas to become actually commercial robots, commercial products. Even though there are a few exceptions, like for example, telesurgery, right? In uh, autonomous vehicles, they're making a significant progress, and I'm sure in the next decade, some of these areas will break through into as commercial products. But for the rest of the semester, we will look at in details into the industrial robots, industrial robot manipulators. Any questions about this generic description of different areas in robotics before we start with the next one? Any questions? Taraka, did you understand everything I just explained about different areas in robotics? Shamal?
Yes.
Okay. Seon? Seon, are you there? Rana Singha?
Yes, sir.
Okay. So now, are you guys able to write brief descriptions about these different areas of robotics? And if I just ask you, okay, give me a 500-word overview of a certain area in robotics, are you able to do that? Ganegidra?
Yes, sir.
Right. Excellent. Okay. In that case, we will move on to the next lecture, lecture 2. Yeah. So, but before this, so let me figure out. Okay. Now, what I'm showing you is the development of the field, industrial robotics, right? You know, there are robots used in various manufacturing industries. Can you name a few? What are the areas in industries where robots are used quite heavily? Can anybody give answers to that question? Tell me a few areas in few industries rather where robots are used quite heavily.
Manufacturing processes.
Uh, there are a lot of manufacturing processes. So, any particular industry? Just give what you think is logical.
Assembly lines like automobile industries.
Automobile industry. That's correct. Vehicles are assembled using robot arms. That's one industry. Any other?
Apparel industry.
Apparel industry. We use a lot of machines, but very few robots. Very few robots. So apparel industry has not seen a lot of robotic technology, but mechatronics and other machines, yes. Any other area?
In military applications.
No, industries. So I'm referring to not applications, but industries. There are different industries, right? Like automobile industry is one. What else?
PCB manufacturing.
Say it again.
PCB manufacturing.
PCB manufacturing. That is electronic industry, right? If you look at a printed circuit board, you can see a lot of ICs, right? These are not all manually placed by people. These are robot. These are placed by robot arms, right? In respective places and then soldered. Yeah, there are many other industries where industrial robots are used, right? So I suggest you to look at over the internet and see for yourself what are the industries where robots are used. What is the major number one area? What is next number two, number three? Right? I'll show you some statistics today. This is a lot of knowledge for you, right? As master students, as professionals, you need to know these things, right? You don't need to just guess. This information is like common sense, very general knowledge for any technical person uh, to be aware of, right? So what I'm showing here is the growth of market robotics from 1994 to 2011, and next slide is 2000 up to 2019 is there. Uh, what do you see? Can anybody guess? Can anybody tell me what's happening here? This is the growth of market according to the International Federation of Robotics, IFR, right? IFR is the place where you need to go, right? If you want to find statistics about robotics, industrial robotics, right? IFR, remember the word IFR, International Federation of Robotics. And they're actually collecting information, right, every year. And this is what they have, 1994 to 2011. What do you see? Any comments? What is on the y-axis? What do you see on the y-axis? What do you see here? Thousands of units, right? Thousands of units. What do you mean by units? So what are units here? The units here are robots. So thousands of robots, right? Thousands of robots. if you look at 1994, the whole world had only probably 55,000 units of robots, 55,000 robots for the entire world. So by 2011, it has gone up to more than 160,000 robots in the world. And now, let's say 2000, we have data only up to 2019. I have to update this one. By 2019, it has gone up more than 400,000 robots, right? This is estimate. Probably the actual one would be slightly different. And you can see the actual the growth rate in the recent times. Last decade is continuous growth, right? And it's about 14% growth, very high growth in the market. So you know the numbers, growth rate, right? And different industries. You don't usually see 14% growth rate in any of the industries. So robotics is an area where very serious, very high growth rate is present. Okay. So if you pedal back, you can see there are ups and downs, ups and downs, up and downs, because you know the whole world periodically goes into recession. People buy a lot of stuff without any control, and then at some point they saturate. They don't want to buy anything because they have enough and more, and markets collapse because people don't want to buy anymore anything. Then after a few years, they start buying again. Then the market goes up again, right? And they keep buying a lot of things more than what they really need, and they hit another peak and they don't want to buy anymore, right? So then nobody buys, and manufacturing industries collapse. The recession goes to recession. So this is how the world works, because the world is not totally controlled, right? You know, it's a free thing, right? Free markets, free, a lot of free things, and no one knows what the other guy is doing. We don't need to know. No, when we purchase something, we don't look at the whole market and take the best decision, right? We never do that. Individuals, families, towns, the countries, they individually take decision. Nobody is really looking at the whole world and take decisions about purchasing, procurement, whatever. Let's say, for example, if you want a car, you collect money and purchase a car. If you don't want a car, you don't purchase a car. Just like that, individual decisions. Right? So when everybody is working like that, the whole world, right, goes bit uncontrolled. No, nobody can be blamed about it. So therefore, periodically you run into recessions, right, like that. So every industry is affected by these global recessions. So not to mention about robotics, everybody is affected by the recession. So therefore, you can see the ups and downs. It's nothing to do with robotics particular, right? So it's a very strong growth rate, robotics. Now you can see here where the robots are actually used, different industries. So this is the estimated worldwide operational stocks, right? Operational stocks of industrial robots, right? From 2013 to 15. Again, this is a bit old. I have to update this with the latest one, but this is also very useful information. If you look at automotive, right, you can see these years, red 2015, ash and blue 2014 and 13. So 13 to 15, you can see the growth of automotive industry. It's about 10% growth, right? Now you have to remember some of these data as engineers, technical people, right? You want to tell your friends, your kids if you have, right, and your friends in conversation. Automotive industry has robots, and these robots, right, as an industry, develop or grow at the rate of 10%, right? This is useful information for people. So one of the things as a technical guy, right, what you need to have is not only the theoretical knowledge, but you need to be able to engage in discussions, right, conversations with other professionals, right, and tell them useful information, right, information that is useful to everybody, right. You don't have to talk about equations, right. When you go to conversation with other professionals, you don't talk about laws and theories, right? But you talk about these numbers, what you see on the screen, right? Uh, Overall effect on the societies and the countries of a certain development in a certain area. So that is why these graphics, these stories are extremely important. Otherwise, you won't be able to engage in any of these professional discussions, right? An electronic industry is next to automotive, right? Actually, you picked up the first two industries correctly. So that's a good job. There you can see 18% growth rate, right? And the metal industry is basically cutting, welding, material handling, and things like that. It's a small, but look at the growth rate is significant, right? So automotive industry is big, but the growth rate is 10. You don't see big industry and very big growth rate. Usually, it's not the case. When the industry is small, you can have a very significant growth rate. You can see over here. Don't have to be, right? But usually, when you see a very big growth rate, the industry is usually at the early or middle stage. When it grows to a certain level, growth rate reduces because there's only so much to grow, right? Chemical and plastics, even food industry, you use a lot of robots. Remember, I showed you the pancake stacking robot, right? That is food industry. Lot of the equipment in food industry will be robots in the future. If not, they're already automated machines, right? Because food is very, like, you need to be very careful in making food, not probably not in Sri Lanka and other parts in this region, but if you go to developed world, right, is a very serious concern, right? You have to make sure, if you are a food manufacturer, right, you have to make sure that food has no contamination at all, and right from the bean bag to the final food package, right? You should make sure that everything happens in very clean environment, handling, etc. Okay, so otherwise you lose your job, right? You lose your market. So machines and robots will dictate this area. So it's like that. Okay, so again, these are thousands of units. So when you engage in a discussion with your other professionals, right, you can actually tell about the number of robots in the world, right? How many robots are there in the world? It's like 400,000 robots, right? You can see these statistics over here, right? You can't just look it up and now I don't know how many, right? So it's better you figure out or remember some of these numbers, right? 2019, 20, 21, 22, probably now it's about 450,000 robots in the world. Okay. Now, if I give you more information, everybody's talking about China, right? For various reasons. If you think about manufacturing anything, the first thing comes to your mind is China, right? Manufacturing. If you have the design in the morning, you can have the product in the afternoon, right? So that is China. They have the whole ecosystem, machinery, everything, right, already built. That is why a lot of people want to go there, go to China for manufacturing. So look at what is behind the scene that you don't see in China. So this is China. When you see it uh, in the industrial robotics domain, right? Annual supply of industrial robots to China, 2010 to 2019. Annual supply. So China does not produce or manufacture robots. They manufacture a lot of things, but still they are not a major manufacturer of robots. They are using robots quite a lot, but they do not manufacture robots just yet. So you see what's happening here, right? They purchase robots. They purchase robots. There may be some manufacturing plants in China, right? But those are not Chinese ones. They are basically like many other industries. Only the factories are there, but they are actually made to the perfection of someone else's design. Okay. And still there are a lot of other manufacturers, robot manufacturers elsewhere in the US, in the Europe, etc. Right? Not in China. So China purchases a lot of robots. See how it has grown. 2010, only 15,000 robots, right? But see the growth. Recently, they are purchasing more than 160,000 robots. 160,000 robots. That is maybe closer to half of the whole world's uh, robot purchase, right? So very significant growth in China because they need for manufacturing industries. They are the world's manufacturing plant, right? So a lot of people go there. A lot of companies are set up there. They need a lot of machines and robots. Now this is the robot density map. Density. Now you know what density is, right? So, but maybe you haven't heard about robot density. What is robot density? Now there you can see the definition. Number of multi-purpose industrial robots, right? All types, all of the industrial robots by number per 10,000 employees. 10,000 employees, right? So if you look at Sri Lanka, how many workers are there? Manufacturing workers, right? Manufacturing industry. Let's say if you have, for example, 1 million, right? So 1 million is about 100 times of 10,000, right? Employees. So if you divide 1 million by 10,000, you get 100. Then look at how many robots are there in the manufacturing industry. So let's say you have 100 robots. So 100 divided by 100 is 1. Okay. So that is the robot density. So if you do that for various countries, this is the map you get. So IFR, they update this data as a major part, major job, right? So there you can see Republic of Korea standing tall, 531 robots per 10,000 employees. So every 10,000 employees, you have 500 robots in South Korea. South Korea. That is the world's highest robot density. So this is very useful information. So in your professional conversations with your colleagues, right, you can share this information with them, right? You become like a very conversant person in robotics, right? When you say, okay, you know what, in South Korea, so you have about 500 or more industrial robots per 10,000 manufacturing workers. That is how you define robot density, and that is world's highest. Okay. So next to South Korea is Singapore. Next to Singapore is Japan. You see, all these countries are Asian countries, right? Closer to us. Then comes the Europeans. Sometimes we think we cannot compete with them. We cannot develop as like in Europe or US. Actually, they come after the three Asian countries, Korea, Singapore, and Japan. Then Germany, Sweden, then Taiwan, again another Asian country, then Denmark, then USA. USA, though, is the biggest number in robotics, right? The density-wise, is not the highest, 176. But it is the place for a lot of robotic research and development because country is so big, they cannot maintain a high density. Then the other countries like in Europe, Belgium, Italy, Spain, etc. So it goes like that. Okay. The other thing I want to share with you is this myth: robotics creates employment, right? The myth is the other way around. Um, when you introduce robotics into your manufacturing industry, and a lot of people say you lose your employment, you lose your job, right? Uh, that is a common complaint, right? So let us talk about it because this is very important for you, right? You need to engage in discussions with your friends uh, about this. So when somebody knows, okay, you are doing, you're studying robotics, they might ask you, you know what, I have heard that robotics will lead to unemployment. Okay, is that true? So if you say, I don't know, then shame on you, right? So you need to have this rational explanation, right? Whenever you say, I know this subject, I learn about this subject. But if you cannot engage in a rational discussion with your colleagues, there's certainly something missing, right? So let us talk about that. So, uh, in fact, robots or robotics create jobs, create jobs. So let us talk about that. How does it happen? Let's say you use, or any country for that matter, use robotics and automation, right? You try to automate your machines, right? Your manufacturing processes, your packaging, your inspection, your assembly, right? Using automation and robotics. When you do that, what happens immediately is reduces cost of production. So you can figure that out, right? It reduces cost of production. Why? Because when you have machines, they are faster, they are accurate, and they are not very expensive nowadays. Two decades ago, robots and machines were very expensive. But now these machines have become affordable to many industries. Affordable. Because you know the whole world, you saw the graphs, thousands of units increasing. Any commodity, when it increases the sales, the cost drops. You know that, right? So therefore, now the whole world has 450,000 robots in the world every year, right? You maintain that number. For the manufacturers, it's a big sale so that they can reduce the price. Okay, so if you use robots now, you can purchase them at a relatively lower cost than what it was a decade ago. Now the robots have become affordable to many industries. Not only they are affordable, they are also programmable easily. You don't need an engineer to program a robot now. A technical guy can be trained for the job. How to install, how to calibrate, how to program a robot, right? Installation, calibration, programming. These are the three things you need to do if you purchase a manipulator. A technical guy can do that. You don't need an engineer. And the machines work 24/7 almost. You don't need to give them a break. You can produce big volumes, okay, and very accurate or perfect specification, high quality, etc., and at a reduced cost, which means you reduce price. Let's say you are a cell phone manufacturer, right? Your cost of production is less. And earlier, cost of production was high. So your price is high because you can't sell anything below your cost of production, right? The cost is high. So not many people were able to purchase. So your market was small. But now you use latest technology, affordable to you. You have some investment, but even that is not very significant investment, not very high investment, and your cost of production goes down. Maybe your cost of production reduces by, say, half. So now you can sell the cell phone at a half price of what you used to sell earlier, right? Now this is affordable to many people. Now the cell phone is an affordable commodity to many people. So therefore, it's not the previous market. Now you have a big market. Okay, now you have a very big market. The market increases. Now everybody wants to purchase a mobile phone. Earlier, even though a lot of people wanted to buy a mobile phone, cell phone, it was too expensive. So a lot of people did not buy. But now cost is half and people can actually give it a try. They purchase it. So immediately, or over a couple of years, because of the technology, the cell phone becomes an affordable commodity to many people. Now everybody is purchasing a mobile phone. So your sales increases. So increased demand because the reduced price. So demand increases. Okay. You can follow this entire line, right? So if you are the cell phone manufacturer, now you see increased demand. Okay, 100,000 units, now 200,000 units, and you forecast in the next couple of months is going to be nearly 1 million. So what you do is you increase your employment opportunities, right? You put up a new factory and you want new people, new employees, right, to run the manufacturing industry. So these are new jobs created. New jobs created. Now, if you look at the first point here, robotics and automation, the moment you bring in robots and automation, you need to ask some people to go away, lay off, unemployment. That happens. Some of the uh, workers, the blue collar ones, right, who were doing dirty jobs, right, are not needed anymore. So you want to ask them to go away, okay, because you have machines. Now you are working with machines. So some percentage of your workers, right, they have to go out. And on the other side here, you are employing a lot of other people. Okay. Some people lose the jobs, but a lot of people get new jobs. So you are reducing your employment here, but you are increasing your employment there. If you combine these two together and look at what happened in some of the industries, the statistics say actually you created the jobs. The total, the jobs you are losing here are different jobs than what you create here. The new jobs you are create here actually are not blue collar jobs, right? But maybe white collar jobs, right? Like technical assistants, maybe engineers, more engineers, inspectors and stuff like that, right? Employment like that. So gradually your manufacturing flow becomes like smart machines, high-end machines, robots, etc. So that is how the developed world works, right? If we do not take this initiative, we will have to stay like with the blue collar jobs eternally, and there will be no progression along this line, and there's no way for you to generate new employment. Okay, so we'll eternally be as we are today. So this is the story about how robotics can change the manufacturing flow, right? And now let me give you some examples. The first one from the automotive industry of the United States from 10 to 15, 2010 to 2015. Over that period of 5 years, right, in US, they have installed 80,000 new industrial robots, 80,000. And they created 230,000 more employees. Of course, they got rid of some of the blue collar workers and they lost their jobs forever. And they employed new people. And if you look at the total net effect is 230,000 more employees. Second example is from Germany, again from automotive industry. Operational stocks increased by 3% on average per year. That is about 30,000 units. All right. And if you look at the increase of employees, it's about 2.5% on average per year. That is about 93,000 employees. So they are also the employment opportunities have not been shrunk. Okay. In fact, it has expanded. But the unemployment, the word unemployment is still there. Okay, some of the blue collar workers, they will lose in this particular examples, two examples. Some of the blue collar workers, they have lost their life, the jobs, and they never got those jobs back because robotics is not going to create blue collar jobs. No, this is a high tech, high technology. It's not going to create lower grade employment. No, it's going to eliminate lower grade dirty jobs, but it's creating smart jobs or better jobs. Okay, so it's very obvious. Now, this one is a very useful information for you to engage in discussions, right? Professional discussions. There again, you don't talk about theories, right? You talk about these statistics, how the world works, how the world is changing with robotics, right? So you need to engage in these discussions, dialogues professionally. So therefore, these numbers are extremely important. Now let me talk about factory roboticization, right? In the developed world, they have done this decades ago. And in countries like Sri Lanka, we haven't done it yet, right? We are still working in the same manufacturing processes we used to have many, many decades ago. The factory flows are not changing much. So this roboticization is a new word in English dictionary. The meaning is to transform manufacturing industries or any other industry for that matter with robots and smart machines, right? So why? What are the major reasons for the increasing demand for factory robotization? There's increasing demand, right? A lot of manufacturing industries, factories and all, the administration really is trying to roboticize the industries. So why? What are the reasons? Number one, declining cost of robots and increasing cost of human labor. Now, even in Sri Lanka, we have felt that. For manufacturing sector, finding labor is getting increasingly difficult. You know that, right? Getting people to jobs is not that easy. Even for the blue collar jobs, right? It's not easy in Sri Lanka because nobody wants to get employed in that kind of dirty jobs, hard jobs. they have other jobs like three-wheel driving, etc., right? Or just being unemployed. That is another choice in Sri Lanka, right? Sri Lanka is a very weird country. Being unemployed is not a big problem here in Sri Lanka. But if you look at other countries, if you are unemployed, you are in a serious trouble. You are in serious trouble. But here in Sri Lanka, even though you are 30 years, 35, 40, 45, your parents will look after you, right? And you don't feel like guilty about it, right? So that is who we are in not only Sri Lanka, this part of the world. But in the developed countries is different. You need to have a job. Otherwise, you are in deep, deep trouble. Okay. So for the manufacturing industry, they need people. If we are not in a developed world, we need to have people to do the dirty jobs. And now you are in a trouble. You can't employ them because they are not there. That is one problem. On the other side, if you look at the robots to replace people, the cost of these robots is decreasing. They are not as expensive as they were. And also, it's not that difficult to purchase and install and calibrate and program these machines. It's not that hard. Therefore, factory robotization, that is introducing robots and machines to industrial premises, is a very feasible, viable option. Number two, robots continue to getting speed, accuracy, capability, and reprogrammability for various types of jobs, such as welding, painting, part handling, cutting, etc. So those are the major processes in manufacturing industry, right? The robots are used for, right? Employed for. And not like those days, the robots now, at present, they have higher speed, high accuracy, repeatability, other capabilities, and also reprogrammability, which means you can purchase a robot and program it for various jobs. You can use it for welding, you can use it for cutting, you can use it for part handling. Of course, you have to change the end effector, the tool, right? If you want to use a manipulator for welding, you need to have a welding torch as the tool. And if you want to use the same robot for spray painting, you need to replace the end effector, the welding torch, replace by a spray gun. And if you want to use it for cutting, you need to have a laser cutter there, right? Like that. Then last point is deployability of robots for tasks that might be dangerous, right? Or impossible for human workers to perform. Like in space applications, you can't send people, right? You need to have robots there. And undersea exploration, search, you need to have robots. And in radioactive sites, and nowadays, COVID infected areas, you saw some of the robots in hospitals, right? Serving food to patients. And also at Morocco, we have built a number of not robots, but automated systems during the COVID period last year. And actually, our team got the first 3 medals at the Sri Lanka Medical Council competition, COVID innovation competition. So Sri Lanka is a country where you have a lot of talent, and people get certificates, gold, silver, bronze medals, etc. Right? But there's nothing beyond that. Every innovation stop at almost every innovation stops at the certificate. Okay, this is pretty bad. To serve food and medicine to COVID patients using autonomous robots, They have a couple of robots, including our own one from Moratuwa. And the patient monitoring system, COVID patients, where doctors and nursing staff should not go closer to these patients because they have virus, right? And you can monitor them, their heart rate, their temperature, their breathing, right? And their SpO2, oxygen saturation. These are the 4 things that you need to monitor of any patient, right? Particularly the COVID patient. And you don't need to go to the patients. And there's an electronic system that we developed, and the doctors, the nursing staff can monitor each and every patient in the ward remotely. And if it is extremely important only, you need to get closer to those patients, right? But we are in a very strange country, Sri Lanka. None of these things, even though we demonstrated, medical council accepted it, awarded with gold, silver, bronze, all 3, it just didn't make the way forward. Just didn't happen. So that's a separate discussion. Therefore, a lot of inventors, innovators, people who want to build things are all disappointed, discouraged. And the government and even medical field people, they always want to purchase things from outside, paying a lot of money, a lot of money, right? That is what they want. That is what they like to do. So that is why Sri Lanka is still struggling to develop, and I don't think Sri Lanka will ever develop in that way. And a lot of people are disheartened, especially the technical people. They don't want to waste their time on any innovation. So, so this is why these are the reasons why the factories, the manufacturing industry would like to go for roboticization, right? Enough and more reasons, right? So that's about it. Now it's time for us to take a break. All right. So in this lecture, I'm gonna give you some basic technical information about industrial robot manipulators. Right. So what are the industrial applications of robots, right? So these are the ones. We use manipulators for palletizing. So what is palletizing? I'll show you in a while. Or unitizing in warehouses, right? In warehouses, this is one of the operations that you do using robots, right? And we use robots for laser cutting. We use robots for arc welding and spot welding and different types of welding. We use robots for assembly lines, right? And there's a lot of list. So let me show you some of the some of these applications, right? So the first one is, say, let's say, take this one. This is palletizing. So I think I need to share this with sounds. Sorry for that. Oh yeah, I have done it already. Can you see my screen? Can you see the video and can you hear the sounds?
Yes, sir.
Fine. So this is a system of palletizing robots, right? There is a front end where you can actually input information. When you do that, this is what's happening on the warehouse floor, right? This is the pallet, the wooden platform on which you stack different commodities. So then comes the robot arm. There is a special type of robot arm. You can see it's a special end effector, right? So this part is actually the end effector, and this is the robot arm, right? So it handles the pallet. And then there's another robot with a different end effector. You can see this arm has a different end effector, okay? And also it has these suction cups. So when you suck air through these cups, this board, which is not a very heavy one, it sticks to the suction cups, right? So that you can move it from here to any other place, like that. So what it does is it places the board on top of the pallet, okay, and it does it very perfectly. And then on the conveyor line, you get the items. What is that? Whatever item, right? In boxes. So maybe the same manipulator with a different end effector on a side, you can use for this one. It stacks on the pallet. So you can see that manipulator, end effector, it has two sides. One side to handle the boxes, the other side to with the suction cups to lift the board, right, and place it on the pallet. So there you can see this end effector is designed to align all the boxes, right, before the boxes are gripped. You don't have to make things unnecessarily complicated. With a gripper like that, with a little push, you can align all of the boxes perfectly. Now, this is very important. After every, say, 2 layers of these small objects, you need to put another board, right? Because it is not good to keep on piling these boxes, right? Too long. So hold on a second. Right. So this every 2 layers of these items, you put another board, because you cannot have this continuous vertical lines, okay, of boxes, because they will fall apart very easily if you do that. This board, after 2 layers, right, or every layer, after every layer, if you put a board, which means you discontinue the vertical line. So if you have lines, you know that in material science, this is some one of the first things you learn about breaking of material, right? If you have the lines, grain lines, at some point of time, there is a crack in any material along the grain boundaries, right? If you have grain boundaries, you can break it very easily. Very much similar here. If you leave the grain boundary vertical, it's very easy to fall apart. So these small the boards, very lightweight, after every 2 layers or after every layer will discontinue this vertical line so that they will not fall apart, right? They will not fall apart. That's done. So now, so please tell me, if you have followed properly, how many robots are there and how many end effectors are there for palletizing? How many robot arms and how many end effectors are there? Any answers? No answers?
So one robo and one infect.
Okay, so if you have one robot arm and one end effector, now how can you handle the pallet? That is one task you have to do, right? So the end effector, how many end effectors you need in a particular operation depends on how many different activities you have to do in the process. So in this process, what are the major activities? The number one, the first one I can tell you is handling the pallet. That is the first task. What is the second task? Handling the pallet. That is number one. Number two, my God,
We can
have you
place
been
the
watching the
boxes,
video? Yeah.
placing the sheet.
Placing the sheet. Number two. What is the third one?
We can place the boxes.
Pick and place the boxes. Is there anything else? No.
Changing the
So,
height and
that's right. So there are basically three tasks here, right? So as engineers, technical people, you need to identify the task in individual activities, right? That is how you design solutions, right? So in order to handle the pallet and then to to pick and place the boxes and then place the board, if you can have one single end effector with different parts of that end effector that you can use for various activities, you can use one robot with 3-in-1 end effector. Okay, so what you need is 3-in-1 end effector and one robot. Okay, so if not, you can have 2-in-1 end effector and another manipulator, another arm with another end effector to do the operation. So two arms will do the operation. It depends on the factory floor where you have the boxes coming in and where you have the pallets, where you have the sheets. Okay, so if you are the engineer who is tasked to design the factory, right, you have to take time and figure that out. What is the most efficient, most cost-effective design for this? If you design the factory floor where you have pallets, the sheets, and the conveyor belt on which the boxes are coming, in a pretty tight configuration, maybe you can have just one manipulator with 3-in-1 end effector to do the job. Okay, so then the plus side is that you have only one manipulator to do the entire job. The negative side is that the manipulator can do only one task at a time. So when he handle the pallet, he cannot handle the arm cannot handle the boxes or the sheet. When it handles the sheet, it cannot handle pallet or the boxes. Of course, you don't need to have handle pallet when you handle boxes and sheets. So you have to look at that. If you bring in a second manipulator, you can combine the activities. When when one manipulator handles the sheet, okay, halfway you can have the other manipulator to bring boxes in, right? So you can speed up the operation, but it becomes a bit complicated. Okay, you have to see whether there's a net advantage or significant advantage of having two manipulators or just one manipulator, and depending on your orders. Why do you have very fast palletizing operation? Do you really need to have very fast palletizing operation? And do you really handle that kind of demand? If not, why don't you do it with one manipulator which is not as fast as having two manipulators, right? So all these things are very, very crucial decisions to be made, right? You have to analyze the problem to a far greater depth before you design the factory flow, right? So that's why I'm showing these videos to you, not just a video. Around that video, I need you to think, okay? As a designer, if you are asked to design this kind of thing, okay, what are the things you need to pay attention to? And how do you come up with the best design? Okay, because it's a serious undertaking. Once you design and build it, you can't undo it. Okay, and you're not going to change it for another 10 years. You're going to use it for another 10 years, right? You have to do it right the first time around. Okay, right. Let's look at another one. This time maybe laser cutting. So you have seen in automobiles, right? The doors and other body parts, the metal piece, right? And you have holes here and there to take hoses, right? And auto electrical wiring and so on, AC, etc., right? So all these holes are cut using this technology, right? Laser cutting. So you can design the whole thing, right? How many holes and their sizes, the location, etc. And then use a 6 degree of freedom manipulator so that you can position the laser cutter, the laser beam, normal to the surface of the metal, right? And cut whatever shape you want, right? So it's a very smart, very advanced technology, and you get very accurate and fast performance. See how fast this is and how accurate the process is, right? Okay. Then what about arc welding?
ABB is not the first, but we have developed the most outstanding arc welding robot on the market. The IRB 1600 ID, the ultimate arc welding machine. I've shown you the top 6 sales arguments for the IRB 1600 ID, which are the long life expectancy of the hose package and that it's easy to replace. The IRB 1600 ID has the highest reliability of all process arms on the market, and the slender profile of the robot with hose package makes it possible to have a high robot density on the shop floor, and thus a higher output from the factory. The slender profile and the enlarged work area of Access 6 ensures excellent accessibility for
Now here you can see the design of the welding torch, right? You can see the bend there, right? Bend there. To be able to weld very complicated objects, right?
inside narrow places,
Welding from outside and inside
and
of
enables
objects,
circular welding
like that.
without interruption or disturbance. The last 2 arguments on increased accessibility makes the programming time shorter for robot installations with IRB 1600 ID than for other robots in arc welding applications.
Okay. So next one is say this one again welding, but this time is a slightly different job. You can see multiple robots working in tandem. So in manufacturing or construction industry, you need to have these beams, steel beams, right? The precast fabrications. You need a lot of steel beams, right? And they're identical, right? Like kits, for example, kits. Well, whole building has a kit. So it has so many of these beams, and people know how to assemble the whole building. So these beams are to be welded, and this is how they do it, right? These robots use vision technology and also infrared or maybe visible ranging sensors. So one robot keeps the object in place and the other one does the welding. It just put the tag, first tag, to hold the item in place. Now the first robot retreat, and the second robot, which is actually the welding robot, it does the job, complete weld, right? So when you have multiple robots, right, working in the same workspace, now see the other robot, right? Other robot, it has to pick up the second block, which is here, right? While the second robot is doing the welding, the first one has already started the work. So it has vision system to figure out where the object is. this metal piece can have different orientations. So the robot needs to pick it up in the right orientation. So in order to pick up in the right orientation, the robot needs to know at what orientation the object is placed. So that is why it uses the vision system. There you are. So the manipulator changes its orientation depending on the orientation of the object, and it picks up the right orientation. So the beam is turned around before welding the second piece. Okay, and this is the turning and positioning of the beam. It turns 180 degrees. So all these things are, if you see, very advanced. They are actually not. They are very simple motion activities, right? So this is the first robot bringing the second piece and placing it at the right place. Then comes the other robot and tag it to the place. Just putting a welding tag to place the object in place. Then the first robot can take the hand off. Right. So now let me ask you a question, simple question. What do you think is the end effector of the first arm? What do you think is the end effector of the first robot arm? Any answers? The first robot arm. Say it again. Your voice is breaking. I can't hear properly.
So it's an electromagnet.
Yeah, we call it electromagnetic gripper. Okay, it just, it doesn't grip it per se, but we call it a gripper because it brings an object from one place to another using an electromagnet. Yes, correct. Then let me show you this one. From Fanuc. By the way, earlier you saw few different robot manufacturers. One is ABB welding robot, and this one is another one, Fanuc. Fanuc is another robot manufacturer. They have family of robots designed for particular applications.
Fanuc Robotics is proud to introduce the new R2000IB 210FS robot. an industrial robot that is unique for its hollow wrist with internally routed utilities and signal cables, making it ideal for applications that require work in tight spaces like servo spot welding, clinching, riveting, and material handling. In this demonstration, the new R2000IB210FS uses servo weld gun control to simulate spot welding inside a truck cab.
Now you see this end effector is yet another one, right? So watch it closely.
The robot's slim wrist is ideal for this tight work area. The development of this robot was in direct response to body shop and fab shop customer needs. Its unique hollow wrist routing.
What do you think is the robot doing? What do you think is the robot doing? Any ideas? What is the robot doing? So this is what is called spot welding. Have you heard of that, spot welding? Spot welding. So in spot welding is if you want to weld two pieces together, two metal pieces together, you can send an electric current from one point, from one sheet to the other, strong current, and then at that point both of these metal parts melt a little bit and then they stick together. The process is called spot welding. So here you can see this robot, right, is going through this car body. You see the window cavities and all that. Along the line, right, there are two pieces together. It holds the two pieces together and sends an electric current from one jaw to the other one, okay, through the two metal pieces, and then the two pieces bonded together.
With internally routed utilities and signal cables, fully support offline simulation, leading to faster system integration through reduced dress out and part programming time. Compared to conventionally dressed robots, this new robot eliminates the need for dress-related adjustments when a part program changes or new parts are added, significantly reducing tryout time and life cycle costs.
And this is also important. After a certain while, right, the robot needs to clean the tips, right, because there's a huge current going from one tip to another. It can corrode a little bit, so it will reduce the current, right, and gradually you don't get the strength in the bond, right? So you need to repeatedly clean the tips.
Additionally, the robot uses IR Vision tip inspection software to verify the weld tip condition. This checks proper alignment to help arc and spot welding customers reduce part manufacturing issues and scrap rework costs caused by poor weld tip conditions. The FANUC R2000IB family of robots has best-in-class reliability and offer a variety of payloads and mounting options. To learn more, please visit our website at www.fanucrobotics.com.
All right, then finally, let's look at the assembly operation. This is from Festo, yet another manipulator manufacturer. This time what you see is a workstation. It's not cutting, welding, or whatever. It's an assembly workstation where the robot needs to handle number of different items and then put them together and assemble a unit. This is the first piece it has to handle. That's the second piece being screwed in to the first piece. This is the third piece. The fourth one. So when the manipulator handles these objects, right? Next to that, you have the same item in a stack. There are so many of these items. These are called part feeders. You have part feeders which submit item by item for the robot to pick up. You've got the spring in place and then the cap. The fourth piece, or the fifth one, I guess. The sixth one. And you screwed in. That's it. So that is the piece. Okay. So how this particular piece is assembled by a robot. It's like assembling this unit with 5-6 different items by a person who has only one hand. So you might think that if you have a person employed here with all these parts in boxes, the person can assemble this one in probably less than a minute, right? Maybe 15 seconds. The person can do this whole thing, right? Then why we need to use robots? Robot takes a little while, right, for the assembly. So to appreciate that, that's a very valid question, right? If you want to do a manufacturing job, you can't exclude manual labor. You can't exclude manual labor. So if it is the most profitable way, you have to go for that. Employ people and give them the parts and they keep assembling. And you pay for that, right? So everything depends on when it comes to commercialization and manufacturing. It all depends on how much you want to pay for that, right? Because that will add to the price of the final product. So if you are thinking of other things like you want to have this manufacturing lineup, right? And you are going to invest a lot of money for that. This is just a part of that. This is not the whole process. There are other things where you have robots anyway, and they are much faster, accurate than humans. And only this part is to be done manually. It just doesn't fit into the system. Because when you have people, there is a serious concern. What if they do not produce the right amount, right? And then the rest of the manufacturing line, which is automated already, right, cannot operate. So there's a risk factor there, right? The manufacturers, they don't like to have any undue liability or risk, right, in any part of their manufacturing lineup. So therefore, to assure that no matter what, strikes or any other things done by the manufacturing workers, right, should not affect the manufacturing process. For most of the people in the manufacturing industry, they want to have the automated system, sometimes at a cost, because it gives them the assurance that they can continue supplying their products to their customers. So there are various reasons as to why you want to roboticize a factory. It's not entirely the financial profits coming out of that manufacturing process, but it is much more than that. Okay. But if you just look at a single operation, sometimes it doesn't look so promising in financial terms, right? That's true. Okay. Now let's get down to the technical details here. You saw a couple of robots, right? You saw a couple of robots doing various tasks. So now, what is common in all of these manipulators, right? So here you can see the robot manipulator consists of rigid links. You saw those, right? Rigid links, number of them, which are connected through joint actuators. And you saw some of these joint actuators. These links are rotated with respect to the previous ones, right? So that is how you position your end effector, okay, properly. Joints are actuated with sensors. You saw that because when you want to turn a joint, you need to know what is the angle now. If you want to turn 30 degrees, what is it now? 25. Then you have to go another 5 degrees, right? So all these joints need to have sensors that you need to measure the angle. Sometimes you want to measure the speed also, joint speed, angular speed, position and speed. If you have a position sensor, you can actually calculate the speed also, right, by differentiating. So these are important for you to control these joints properly. Okay. So according to IFR, the definition of a manipulator is an automatically controlled, reprogrammable, multi-purpose manipulator, programmable in 3 or more axes. 3 or more. Why? If you have just 1 or 2, it's a question whether it is actually a robot manipulator. It's too simple. When you have 3 or more, it becomes a bit complicated because you have to get it closer to human hand. So here the industrial manipulator word has something to do with human arm. So if you look at human arm, you have the shoulder, you have the elbow, you have the wrist. Don't worry about fingers, right? These joints, they are sometimes just 1 degree of freedom joints, some are 3 degree of freedom joints, like that. It's a complicated structure. So the robot manipulators that we discuss here are not that complicated, but there should be some similarity to human arm, right? So that is important. So in robotics, constant monitoring of positions and orientations of manipulator links. These are the links, right? These are the links. The tools and objects it handles, right? And other objects in the vicinity is essential. You need to have constant knowledge and your visibility about these links, the end effector, and what is around you at all times, right? Because you cannot bring the end effector to collide with the robot itself. Right? You can't kill yourself, right? Robot can't kill it, right? And also it cannot collide with the nearby obstacles. So therefore, it's a complicated mathematical process that you have to run every second, maybe many times a second, to look at where the robot is, where the other objects are, right? So you have to do this continuously. So now here you can see a manipulator with first link, second, third, fourth, fifth, and sixth. 6 links. Okay, so we call it a 6 degree of freedom manipulator, because every link, right, is connected to the next link through a joint. One joint means usually 1 degree of freedom, one variable in the manipulator. So if you look at this manipulator, and if you look at this as a mathematical equation, it has 1, 2, 3, 4, 5, 6 variables. It's like a multivariable function. This manipulator is a function of 6 variables. So we call it 6 degree of freedom manipulator. So you can change any of these variables, any of these angles, angle 1, 2, 3, 4, 5, 6. Then you get a end effector, position, and orientation. Okay, this is the end effector. What is this position in X, Y, Z, 3 dimension? And what is this orientation, whether it is looking up, down, left, right, or whatever. So you need to know position of the end effector and the orientation of the end effector. And to know it and also to control it, how can you bring the end effector to a certain point, let's say somewhere here, with a certain orientation. Okay, in the laser cutting, in the welding, you saw how the manipulator is brought into that position. Okay, how the manipulator is brought into that position and orientation. So getting to a position is one thing, but getting to that orientation together with the position is quite another, right? So you have to do this simultaneously. How do you do that? So we can talk about that maybe later. We call it path planning, trajectory planning, how you bring the manipulator to the desired position and orientation, okay, before it can do whatever it intends to, welding or handling, part handling or whatever. But with 6 degrees of freedom, 6 variables, you can do that. If you have only few variables, maybe 3 of them, you can't control the end point and position it with the correct orientation, desired orientation. With only 3 joints, you can't do that. In order to orient it properly and control the position, you need about 6, right, degrees of freedom. Now, if you look at manipulators, most of the manipulators that you saw in the videos are all rotary joint manipulators, rotary, right? If you look at your hand, upper arm, right, lower arm, or forearm, right, fingers, they're all rotary, rotation, right, between 2 joints. And there are sliding joints also, sliding joints, where the length changes, not rotation, right? I will show you some of the videos for that. And for rotary joints, this is the symbol. When you want to draw a manipulator, right? You don't draw it like what you see physically, but using these links and joints like that. First link, second link, and this is the joint. This is a rotary joint. Whereas if you have a prismatic joint or sliding joint, like a lead screw or something, this is how you draw it. You have this damper kind of illustration. You have the first link, you have the second link, and there's the motion, like piston motion, right? Piston, sliding joint. Now, the manipulators that you saw are actually called serial link manipulators. Serial link manipulators. Serial means you have one link, and at the end of that, you have the next link, like over here. The first link, which is the zero link or link zero, which is actually the base, which is not moving. And then you have the second one over here, right? Second one over here. And there's a rotation like that. Second link rotates horizontally with respect to the first link. Okay. And then the next link rotates around the second link, right? Or let me call it this way. The first link rotates around with respect to the base, and the second link rotates with respect to link 1. The third link rotates with respect to link 2, like that. Every link rotates with respect to the previous link. Okay. And they're connected like that. Second link is connected to first link. Third link is connected to second link, like that. This is why it is called serial link manipulators. So there are other manipulators where it is not serial. You will see it later, right? But most of the manipulators we are going to analyze in this module are serial link manipulators. Okay. So non-serial closed chain manipulators are there. I will show you some of them. We are not going to analyze them here, right? So most of the industrial robots are serial combinations of revolute and prismatic joint, serial combination. Okay. So one after the other. You are not going to connect the end effector back to any of the other links, right? It's not like that. So most fundamental functional requirements for a robotic system is to be able to locate its end effector, that is the hand, tool, or end device, in 3D space with respect to the world coordinate frame. So you have the world coordinate frame X, Y, Z, and you have to position your end effector at a certain point with a certain orientation. So that is the most fundamental functional requirement of any robotic system. Okay. And there are 6 different types of manipulators, right, that you can see in the industry. These are the 6 names: Cartesian, cylindrical, spherical, SCARA, and articulated. There are 6 different types, right? You may have heard some of these names: Cartesian, cylindrical, and spherical. You know, these are coordinate frames, right? You have studied in mathematics Cartesian coordinate frames, cylindrical coordinate systems, and spherical coordinates, right? These manipulators are actually designed similar to the coordinate frame itself. That is why they are called Cartesian, cylindrical, spherical. And then you have some unique designs like SCARA, selective compliance articular robot arm, that is SCARA, and then articulate robots, so rotary, all rotary manipulators, right? So we're going to look at each and every one of these things, and our analysis is actually based on articulate robot arms, which is the most complicated one out of all these. Right. So, yeah, before we get going with the links, I think this is a good point to wind up today. So I think it's time. Yeah, we don't have much time. Maybe we can go for one or two. Let's take Cartesian robot. Yes. So this is the Cartesian coordinate robot. In Cartesian coordinate system, you have three coordinates, x, y, and z. They are orthogonal to each other. It's an orthonormal coordinate frame, Cartesian coordinate system. When you change x, you don't change y or z. When you change y, you don't change x and z. So you can keep any of these two coordinates unchanged and change the other one because they are normal to each other, right? It's very, very simple. Because let's say when you change one of these coordinates x, if it changes y and z, you are in trouble, right? You are in trouble. How can you control x, y, and z as you wish? It's difficult. It's difficult, right? So this is the most fundamental x, y, z coordinate frame. And if you look at these joints, they are linear joints or sliding joints. So x moves this way, y this way, z this way, vertical. So these joints are not rotary, they are sliding or prismatic. And in this particular case, we have only three joints, x, y, and z. So then we use symbol P for prismatic joints. And we have three prismatic joints here, P, P, P. So therefore, we call it PPP, Cartesian coordinate robot. So if you want to control the endpoint here, any x, any y, any z, you have to individually drive x, y, and z to that position. Individually drive to that position, okay? And it's very, very easy. No serious mathematics involved, independent controls of x, y, and z, okay? You can have three stepper motors to drive three axes, x, y, and z by whatever amount you want, and you get to end effector to that point. Very easy. So what are the applications? Pick and place. Pick and place. If you want to pick up an object from one point and then bring it to another point and place it, you can do it very easily here. Right? So let me show you a video. Yeah. So you saw that pick and place, right? Using three axis Cartesian coordinate robot. So in this particular case, what about the orientation? So x, y, z means position basically. Now, if you want this robot to, so let me show this again. You can see right there. Now this arm is, you're going to use the arm to pick up this object. Okay. You're going to use this arm to pick up the object. Now see how it happens. Right? And look at the second one. See, do you see any orientation control here? Yes or no? Do you see any orientation control of the end effector before it grips the object?
No.
No. It is blind to the orientation of the block. What if these small objects, black objects, are randomly spaced around? Will it be still able to pick up the objects in the right orientation? I don't think so. Maybe there's no need to pick up the object in the right orientation. Okay. So this is just to demonstrate X, Y, Z. But if you are doing a serious work where you need to pick up, before you pick up, you need to know the orientation of the object, whether it is aligned along X direction or Y direction, or whether it is at an angle, then you need to rotate the end effector. You need to rotate the end effector like that by a certain angle before you can pick up, right? So then you are adding another degree of freedom to the XYZ. So XYZ is basically position. And then you add another motor here, servo motor, to turn the end effector like that by a certain number of degrees. And that is your fourth joint. Okay, fourth joint. So it becomes a 4 degree of freedom manipulator. And after that, the gripper, we don't call it another degree of freedom. It is just gripping, right? It's just the tool. In the previous case, you saw welding, cutting, etc. These are the tools. A tool is not a degree of freedom, but if you use any motor to control the position or orientation, that is a degree of freedom, right? If you use any other motor to grip or a relay or electromagnet or anything, that's not a degree of freedom. That's to do the job, right? But to get there, to position yourself and control the orientation, if you use any number of motors, they are all degrees of freedom, okay? Right, fine. So there are a lot of applications, and I request you to learn, read about this material. I will make it available, right? A lot of things: screwdrivers, automatic drills, dispensing heads, welding boards, welding heads, grippers, cutting heads, etc. There are a lot of things, right? The second type is basically cylindrical coordinate robot. Now there you are. So let's look at it. So okay, before that, see this illustration here, right? The robot is like this. So it has a Z direction, right? Actuator to control the height, vertically, move vertically up or down, right? And then move horizontally in and out. So vertical motion and horizontal motion. So they're both linear, right? So vertical motion, horizontal motion. So they are normal to each other. So you can change Z without changing Y. They are normal to each other. And then you have this rotation. You have this rotation. So you have a rotary joint. For the first time, you see a rotary joint. Rotation around the Z-axis and moving along the Z-axis and stretching in and out. So there also you can control the position and orientation in some way. You don't have complete control, right? For example, when you turn this Z, you control the orientation. Okay, but you cannot control the orientation at any X. right? So you can control Y, that's okay, but the X is the other way around. So always your heading is along Y, okay, this axis. So this is constrained orientation control, constrained orientation control, because obviously you have 3 degrees of freedom, right? Whatever you can do, right, is basically from 3 degrees of freedom. You don't have complete orientation and position control at the same time, right? So let's see this video. So this is the Z axis, up and down motion, and this is the rotary motion. This is the rotary motion, 2nd degree of freedom. This is the third one, Y. So now you probably are beginning to understand that the particular type of robot manipulator that you need to use depends on what you really want to do, right? You have to look at what is the job, what is the task, what is the activity, and then what is the most appropriate manipulator to do the job. If you can do the job with a fewer number of degrees of freedom, go for that. For example, if you can do the job with a Cartesian manipulator, XYZ, which is the most simplest and probably the cheapest to purchase, go for that. But be mindful about the limitations of the manipulator, right? If the limitations is going to restrict your operation, don't go for that. Think about a different type, say cylindrical or spherical, whatever, right? But you don't have to go for articulated manipulators. 6 degrees of freedom, all rotary, bit complicated, right? If you don't really need the full capability of that kind of manipulator, right? Okay. Right, so it's time to wind up for today, and I'll continue from here next week. Have a good evening.